Start.
All right, so this is because we had a snow day. Sorry about this, but the show must go on. So last time I started using the coordinate mapping, right? Now we defined the coordinate for a basis back earlier, but I didn't talk about it in terms of linear transformation. That's what I'm doing now. So let V be a finite dimensional vector space. All right, and basis with basis beta equal to, let's say, v1, v2, dot 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 vn. Then the coordinate map phi beta. It's a mapping from the vector space V to Rn, since we're dealing with real vector spaces here. And it's defined by, well, I could just say it's defined by saying phi beta of Vi equals to Ei extended linearly. In practice, that's often what I do. All right. And we put that in parentheses. That's one way you could define it. But that, of course, is equivalent to just saying the following phi beta of x1 v1 plus x2 v2 plus dot 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 plus xn vn is equal to x1 e1 plus x2 e2 plus dot 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 plus xn en, where that's the standard basis. Of course, the right-hand side we can also write as x1, x2, xn in the usual notation. And that's true for all v in v. All right. So what are the properties of this coordinate mapping? Well, you know, it's linear, all right? It's a surjection. It's an injection, so phi beta is in fact an isomorphism. Phi beta is this sort of canonical isomorphism. Well, it's not canonical. Canonical means that you're saying something without respect to a basis. I mean, phi beta is sort of the height of non-canonical. I mean, it's very much with respect to a basis, right? I mean, that's kind of the whole thing. But certainly, anytime you have a basis, you can construct this coordinate map, and it gives you a way of trading the abstract vector space V for this very concrete set of column vectors, right? So, without me, I'm going to repress my urge to prove those things I just said. They're not hard to prove. I'll leave those to you. So that's why we have tests. All right, example. Let me just go over a couple of examples to get us going on this. V equals to R 2 by 2, and let's the basis beta equal to 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So this is a choice of basis for our 2 by 2. Usually this would be what we call E2-2, right? This is, on the other hand, here's E1-2, etc. All right, then in this case, the coordinate mapping of A, B, C, D, so labeled, would just be actually A, B, C, D. Because, of course, I can write this as a sum of A times this, plus B times that, plus C times this one, plus D times that one. That's the coefficients of the linear combination. So that's the coordinate mapping there. Another example, let me erase the definition. So. Another example. Example 7.3.3 for what it's worth. You look at V as the complex n space. So this is n component complex vectors. You could look at it as a real vector space, viewed as a real vector space. Okay, so what does that mean? So if V is an element of big V, that implies that V is equal to x plus I times y, where x and y are n-dimensional vectors. Let's see here. So let me see. What else could we define? Well, you can also define the complex conjugate for an n-dimensional complex vector. Like what's v bar would be x minus iy, right? Okay, so like if I look at v plus v bar, what do I get? I get 2x, yeah. And if I look at v minus v conjugate, I get 2iy, right? So this suggests to me then that x is equal to 1/2 of v plus v bar, and y, yeah, 1/2i v minus v bar. Excuse me. So if I wanted to define, I could define this as a coordinate map, I think. So phi beta of v will be equal to 1/2 v plus v bar, comma 1/2i v minus v bar. So this would be an element of Rn, which is of course R2n. So there's a coordinate map. Now the question is, the coordinate map, I didn't ever write the basis. Well, what basis is this with respect to, right? Now, every once in a while you can write down a formula for a coordinate map without even exhibiting a basis, right? And obviously this begs the question, what is the basis? You know, so good news, you can work backwards, right? So in particular, I can look at, you know, what's phi beta. Let's see here. Suppose phi beta v is equal to E1, for example, right? So that would be like 1, 0. Oh, I'm not getting to the point very quickly here. Curses. I mean, this is a little bit misleading. There's 2n minus 1 zeros here. Oh, okay, but in any event, you know, if the basis for v, all right, let's say the basis for v is equal to, say, f1, f2, f2n, right? Again, we don't know what those are just yet.
4:00 p.m.
By definition, phi beta of f1 is equal to E1. That's the very definition of the beta coordinate mapping. So I know what E1 is, right? And I can calculate what's the inverse. Well, that's the thing. I haven't calculated the inverse yet. That's where the rubber hits the road. So f1 is equal to phi beta inverse of E1. So the question is, what is the inverse mapping? You know, can we find the inverse mapping of beta? I think we can. Once I write something, you're going to be like, well, duh. Perhaps you guys are already saying duh in the comfort of your own dorm room or whatever. So this is supposed to be x, and this is supposed to be y, right? So maybe phi beta inverse of x comma y should, I don't know, maybe it should be x plus iy. What do you think? I'm pretty sure that's what it should be, because that was how we constructed it. So that's actually the inverse mapping. You can check it out. You can try it. I mean, you can take it for a spin. compose phi beta with phi beta inverse, and you'll see that you'll get back where you started, and therefore it's the inverse. Won't go through that, it's not too exciting. Once you know that though, let's see here. So phi beta inverse of what? Of E1, but another way to write E1 of course was what? 1, 0, da 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 0, comma 0, da 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 0. So this is like my x, this is like my y. So x plus y is, it's just 1, 0, da 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 0, n of these, all right? And I'm tired of this example, so I'm going to tell you the answer. So if you keep working this out, what you're going to get is that beta is equal to E1, E2, da, 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 En, and then I E1, I E2, da, 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 I En. So it's basically the standard basis and then the imaginary unit times the standard basis. That's the basis with which with respect to which this is the coordinate mapping. So it's kind of a weird example in the sense that I don't state the basis at the start, I just come up with this formula. But anyway, I'm going to go on because this is somewhat of an outlier in my examples. You are, of course, free to ask me questions about that if this was not clear. Oh, well. I guess I should have asked you if everything was in frame before I did that. Okay. Okay, so another example. Another example of coordinate maps. If v is equal to nth order polynomials, and oh, pause.
No, I can't.
You can't pause.
No, I can't.
Oh, thank you. I'll take it. Yeah, all right. My own stupid fault. Okay, so beta is equal to 1 x minus 1 x minus 1 squared all the way on out to x minus 1 to the n power, right? You can say, well, you know, what's the find the coordinates, the coordinate mapping on f of x, where f of x, what is that when f of x is equal to, you know, to make our life inconvenient, we'll put f of x in its standard form. Okay, so we got a little bit of work to do. We have to somehow recenter. We have to recenter this polynomial, right? In order to figure out what the coordinate mapping is, right? So, okay, but that's not hard because we know that we could say what? We could say Taylor's theorem, right? So what I need to do is express f of x as a sum of these guys, things in the basis, right? So f of x is actually equal to what? It's equal to the sum n, ooh, n's a bad choice, k. We don't really need a Taylor series. Taylor polynomial will do because we're only going up to nth order here. K equals 0 to n of the kth derivative evaluated where? Well, 1 over k factorial times x minus 1 to the k, right? In other words, f of x is equal to f of 1 plus f prime of 1 times x minus 1 plus f prime prime of 1 over 2 factorial, x minus 1 squared, plus plus the nth derivative, and evaluated at 1 times n factorial, x minus 1 to the n power. And aha, that tells me what the coordinate map is then of that. So I can read it off. I can say, aha, the coordinate map of fx with respect to this choice of basis beta, it's just f of 1, f prime of 1, and this is missing in my notes right now, 1/2 f prime prime of 1. Dr. Professor Landon, look at that right there. There's something to tell you about. And let's see here, and then 1 over n factorial. I'm missing that in the notes again. So there you go. That would be the coordinate mapping in this case. So
I see. Huh. Nice.
these examples are these examples are actually considerably harder than the ones we'll work with for actual linear transformations. I think it's good to see some harder examples. So let me continue with my punishment. Well, it's not a punishment, I'm just... Ooh. You can see all that, right?
What?
We can see all that, right?
Yeah.
Okay.
Why?
Yeah, it's a little late to ask, but... Alright. Continuing. Alright. Exercise 7.3.5. Here we're going to look at a really kind of weird set of things. V is equal to, let's see here, A in, oh, this is really weird. This is a really strange set of things. A equals the sum ij 1 to 2 of aij eij. Okay. This is a really weird example. Such that what? Okay. What I've got is I've got a11 plus a12, a22 rather, equal to 0. And then I've got, where are those? Oh, and then I tell us that a11, a21, and a22, these are all complex numbers. And then just to be really weird, I have let a12 be a first order polynomial. And that's a weird example. Okay. So let's see here, just to be clear, what does a typical thing look like then? A, an element of V. That means that A looks something like the following. It looks like A plus IB for the 1 spot. See the first condition up here, A11 plus A22 be 0. That makes this be minus A minus IB. There's no condition whatsoever on A21 except that it's a complex number. So I would just do
C plus ID.
I have done X plus IY just to be annoying, but yeah. And then, then up here, it's just a first order polynomial. And I'm going to view it as a subset of the polynomials in T, since I used X in a different way already. But say C, CT plus D, yeah. So this is a generic object, element rather, of V. So a natural choice of basis here, in my humble opinion, and you could put these different orders if you want, but this is definitely what I would do if for some odd reason I was working with such an example, and could. So first of all, I would do 1, 0, 0, minus 1, and then I would do I, 0, 0, minus I. That takes care of the diagonals. Then I would pick up, for some reason I've done the polynomials next, so 0t, 0, 0, 0, 1, 0, 0, that picks up the 1, 2 component, and then finally I take care of the lower 2, 1 component.
0, 0, 1, 0, and 0, 0, I, 0.
Right. There's a basis, right? And with respect to that basis, the coordinate mapping of A is simply the following. So I need A of those. I need B of these guys. I need C.
Wow.
It's almost like this was on purpose. I need D of those guys.
And X.
Oh, yeah, X.
And Y.
And Y. Yeah. There you go, that's the coordinate mapping. All right. So I hope that gets us started on the concept of a coordinate map. All right, that's kind of that's the basic thing here. My examples are pretty weird. What you actually face in the problem sets, I think by and large is easier than what I've just done. So I'm going to go ahead and erase again. All right, so finally we have the nice backdrop we need for the real point of this section. The real point of this section, the part I'm going to bother to talk to you about today, I will go over the computational aspect of it. Probably go over a little more theory on Monday. Is the matrix of a linear transformation. All right, so suppose you have a linear transformation. I use T in this section. So T from V to W, a linear transformation, all right? And we're going to suppose that V has basis beta and W has basis gamma again, all right? Mm-hmm. Now, basically this is the thing. I can look at this picture and understand how to go. I've got V, T, takes me over here to W, all right? But, you know, I can't write a mapping directly from V to W just as a matrix multiplication, because V and W may be sets of matrices themselves. They could be polynomials, they could be functions, they could be all kinds of crazy stuff. I can't just write matrix multiplication. I can't realize this black arrow as a matrix multiplication many times. However, what I can do is I can use coordinates. See, I can take the beta coordinate mapping and I can go down here to Rn. Well, let's suppose that this is n dimensional. And let's suppose that this is m dimensional, okay? So W is m as in mummy dimensional, and n as in, V is n as in nanu dimensional. And then, let's see here. Over here, so Rm, Rn, again, this is V, this is W. All right. So let's see here. I also have an inverse mapping over here, right? I can go up like that. I can go phi gamma inverse like that. So, and this is the T. So basically, if you think about it, we ought to be able to build some kind of mapping downstairs. Now, down there, this is the world that we know and love from earlier, part 1 in the course, right? Here we're looking at a mapping from Rn to Rm. By the fundamental theorem of linear algebra, if this red arrow is a linear transformation, we know we can write it as a linear transformation, right? Matrix multiplication. So, and that in fact essentially defines the matrix of T. So we say linear transformation of the matrix induced T, beta gamma is my notation. It's not a great notation, there's a better one. But basically, this picture, in some sense, defines the matrix of the linear transformation T. So I'm going to write a few formulas for this, and eventually we'll get around to the point of giving a specific definition. But I mean, in some sense, this picture is the definition of T. You draw this picture and assume that the diagram commutes. That essentially forces you to define the matrix a certain way. But here's some formulas that are true for it. So let's see here. I can say that the matrix multiplication of T beta gamma, that this map is the same as going, oh man, well, to go the opposite way I have to do what?
Beta inverse.
Yeah, beta inverse. That's the first. So here's the annoying thing about composition of maths. The first shall be last and the last shall be first. So I got to write that one first.
Mm-hmm.
Then I do T. My guys might notice I'm writing manga style right now.
Mm-hmm.
And then finally I come back down over here.
Gamma.
Phi gamma.
Mm-hmm.
Yeah. So that's one way to look at it.
Mm-hmm.
Now, okay, of course, or you could look at this the other way around. You could try to write T in terms of the other mappings, right? So I could say T is equal to what? Well, T is equal to phi beta. Again, the first shall be last. composed with this this L of this matrix. Sorry, it's getting so small. It's the same matrix. It's always the same matrix. Okay, guys.
And figure my inverse.
Yes, right. And composition here, right? So, does this mapping L have to be linear? Yes, absolutely L has to be linear, because it's the composition of an isomorphism, another isomorphism, and a linear transformation. But we know that the composition of linear transformations is once more a linear transformation. So this has to be linear, which means it makes sense to say that it's induced from some matrix multiplication. Okay, that's first of all logic like that. That's fine. Yet another way to look at this is as follows. My picture's getting a little bit too cluttered for this, but I need another color. Sometimes I like to look at this in terms of, you start with a point up here, let's say x, all right? And that gives you down here the coord, well, x is a bad choice of letters. Let's say you start with v, and then down here you get the beta coordinate of v, right? And then if you multiply, multiply by the matrix over here, we get t beta gamma times v beta. Let's see here. But on the other hand, if you trace up here, so this is matrix multiplication, right? On the other hand, if you follow v on the upper part of the graph, you go from v maps t under v, you get to tv, right? And then if we look at tv under the gamma coordinate going down, that gets us down to the gamma coordinate map, the gamma coordinate of tv. But these two things have to be equal. So another way of defining this, and this is often actually how I calculate specific examples for you guys, is this, is that the gamma coordinate of tv is equal to the matrix T beta gamma acting on the beta coordinate vector V. So this is often how I actually think about calculating things. Although you should be annoyed that I have, of course, not yet defined the matrix T beta gamma, except implicitly. So let's be more explicit. So how do you calculate the ith column of the matrix here? Well, if we just act both sides on EI, then if I take T of, well, just getting to the point here, T beta gamma acting on EI, that should be the ith column of this matrix, right? But on the other hand, that's the same as this linear transformation acting on EI, which means that's the same as phi gamma of T of phi beta inverse of EI. But what is that? Phi beta inverse of EI is exactly VI. I mean, I guess I should declare notation here. So letting beta equal to, say, V1, Vn, right? And if we need it, we'll write gamma is equal to W1, Wm. So this is, by the definition of the coordinate map, that is exactly, VI. Right. So there you go. That's a definition, if you like. The ith column of T beta gamma is simply equal to the gamma coordinate mapping. Well, I guess I mean, a different notation you can choose here. It's the gamma coordinate mapping of T of VI, or if you prefer, you could write T of VI gamma. I'm not sure that's actually the definition I gave in the notes now that I write that. Oh, I just say it's implicitly defined by the diagram, essentially. There is, let me just, one more equation, then I promise I'll stop and actually do an example. So this is sometimes really nice to look at this a little bit more explicitly. What this is saying the matrix of T with respect to the beta gamma basis choice. It's this matrix. It's you take the T acting on the first basis vector of beta, and you look at its coordinate with respect to the gamma matrix, gamma basis. And then next you look at this image of the second basis coordinate in beta, and you look at its coordinate in the gamma basis, and so forth, until you get to the nth basis vector, and you look at its gamma coordinate, and this is, you know, some books will use this as the definition even. I don't know. You know, you pick what you like. It really is better to understand the picture and be able to attack it from many different directions. By now you're probably confused.
Yeah.
Yeah, probably. My picture's gotten a little bit busy. Let's look at an example. That will help.
Should we pause?
Should we pause?
Yeah.
Yeah, sure.